Hello, my name is Hong Jin, and now I will present our work entitled Active Learning of Discriminative Subgraph Patterns for API Misuse Detection. Modern software systems rely heavily on third-party libraries, and to interact with the libraries, the software systems use the APIs that are exposed by these libraries. The APIs may impose usage constraints, and the violation of usage constraints of the APIs are known as API misuses. API misuses may lead to bugs and vulnerabilities, and therefore it is important for us to detect them. In a prior work, it has been suggested that we could mine and identify usage constraints across projects on GitHub by first converting them into graphs. Next, we can then use frequent subgraph pattern mining to identify subgraphs that represent usage constraints. In this example, we see a subgraph representing a usage constraint on the map interface, which is from the Java standard library. Here, using frequent subgraph pattern mining, we have obtained a subgraph pattern that indicates that the return value of map.get should be followed by a null check. That was the direction proposed in the state-of-the-art work. So given these subgraph patterns that represent a usage constraint involving a null check on the return value of map.get, we could look for misuses by looking for deviations of these patterns. We could look for usages of map where map.get is invoked without a subsequent null check, and then use other heuristics to rank and filter them. In this study, we suggest that the prior work are affected by two assumptions. The first assumption is that frequent code is correct code, and the second assumption is that code that deviates from frequent code is incorrect code. And in this study, we take the perspective that these two assumptions may be unreliable. Alone, GitHub may not be a reliable teacher because frequency may not equate to correctness. The first example for this is that there are many wrong examples on GitHub. For example, it is well known that many usages of cryptographic APIs are misuses on GitHub. Here we see an example where cipher is initialized with the DES algorithm. Today, we know that the DES algorithm does not provide all the security properties that we would expect of a cipher, but if we were to try to learn how to use a cipher from GitHub, we may incorrectly learn that we should initialize a cipher with the DES algorithm. The second reason is that frequent patterns may not represent usage constraints. A common pattern that we see on GitHub related to the usage of the map interface is that the return value of map.get is often printed to standard output. As such, if we were to mine patterns from GitHub, we may incorrectly think that the printing to standard output is a usage constraint of map. In other words, there are many common patterns on GitHub that are unrelated to correct usage. In this study, we attempt to reduce the reliance of frequency, and to do so, we transform the task into a supervised machine learning task, and we involve a human annotator for supervision. We ask the human annotator to label each example on GitHub to determine if it's a misuse or if it is correct. However, this requires substantial human effort and is impractical. One cannot possibly expect a human annotator to label every example on GitHub. To address this issue, we use the principles of active learning and we query the human annotator only for labels of informative and representative examples. And we present our approach that we term ALP, short for Actively Learned Patterns. We start off with a database of API usage examples, say examples collected from GitHub, and our goal is to identify a set of discriminative subgraph patterns. To begin, we ask the human labeler to label a small number of examples as misuses or correct usage. Next, we transform them into graphs, but one difference in our work that differs from the prior work is that some graphs will now have a label attached to them that indicates if they are a correct usage or they are misuses. Then, we mine discriminative subgraph patterns. Discriminative subgraph pattern allows us to identify subgraphs that appear statistically significantly more frequently in graphs of one class than another. In this case, we would be able to find subgraph patterns that appear more frequently in correct usages or misuses. So these subgraph patterns are then more likely to be usage constraints. Based on the discriminative subgraph pattern mining process, we then select informative and representative examples for a next round of labeling. So the human labeler then labels the selected examples, and this process continues where we continue to find a next set of discriminative subgraph patterns before selecting a next batch of examples to label. This process continues until a stopping criteria is reached. The process ends when the human labeler has labeled 5% of the dataset, or if 95% of the examples have been covered by the discriminative subgraph patterns that we have mined. At the end of this process, we would have a set of discriminative subgraph patterns. Next, we describe our criteria of informativeness and representativeness. We wish to select examples for labeling based on these two criteria, and with regards to informativeness, we look for patterns that allows us to say something about the unlabeled examples. In other words, we try to pick examples that are not similar to examples that are already labeled, because our goal is to be able to say something about patterns that explains allows us to say something about the examples that have not been labeled yet. In terms of representativeness, our goal is to avoid outliers, and therefore we pick examples that are similar to other unlabeled examples. We express these constraints as a logic program, and we query the logic program to obtain the next set of examples to label. The logic program encodes the examples, the patterns, and which pattern are matched by each example. And then we select the examples for labeling such that they will match a set of patterns that match our criteria of informativeness and representativeness. Graphically, this is what the process looks like. We wish to obtain the set of examples that we should label such that when they are labeled, they allow us to say something about some patterns that would allow us to say something about many examples or graphs in the dataset. So this is all encoded as a logic program, and we also wish to avoid unrepresentative patterns. For example, if we have a pattern that just covers one example, then it is not very interesting, and we try to avoid trying to find out about these patterns. Next, our goal is to be able to classify new unseen examples at a testing time. Therefore, given a testing example source code, we want to represent it as a graph, and then subsequently represent it as a vector so that we can pass it to a machine learning classifier. To convert it into a vector, we use the discriminative subgraph patterns, and each subgraph pattern is a feature. So we construct a vector such that each vector has each element in the vector corresponds to one discriminative subgraph feature, and the element in the vector indicates if the subgraph pattern matches the graph. So this is the process graphically. Given that we have a program to classify, and we have a list of discriminative subgraph patterns, our goal is to construct a vector V. And the vector V consists of ones and zeros. 1 if the subgraph pattern is a subgraph of G. So first we obtain G by converting the program into the graph. And then we enumerate over the discriminative subgraph patterns. If the subgraph pattern is not a subgraph of G, then the vector is filled with 0. Otherwise, if the discriminative subgraph pattern is a subgraph of G, then we fill the vector with 1. And this process continues for all of the elements of the discriminative subgraph pattern. And this gives us a vector V. And then the vector V can now be passed into a machine learning classifier. However, we still cannot characterize the entire space, and we wish to refrain from classifying uncertain cases because this would waste the developer's time and effort in inspecting the cases. And therefore we use a paradigm known as classification with the reject option. If we are certain of the prediction, we produce the output. Otherwise, we would abstain from the prediction. To do so, we use an off-the-shelf novelty detector, and we compare the testing instances with the training examples. If the test instance looks too different from the training examples, we then refrain from the prediction and we do not produce a prediction. For example, given that the training dataset consists of usages of cipher, and we have seen that the cipher can be initialized with AES or DES. If at testing time we see a cipher that is initialized with RSA, our classifier has no way of making a good prediction because it has not seen this at the testing time, and therefore this looks very different from all the training examples. And as a result, our classifier would then refrain from the prediction because it is too different from the training examples. So this is an overview of how the classifier works in summary. After we have constructed a feature vector V, we then pass it to the novelty detector, and the novelty detector could reject the classification if it turns out that the test instance was too different from the training examples. Otherwise, it is then passed to a binary classifier, which then outputs the final output of ELP, which indicates if the test instance is a misuse or is correct. At a high level, this is what ELP looks like. We first try to obtain the discriminative subgraphs through multiple iterations of labeling, and then after we have identified the discriminative subgraph patterns, we can then use it at test time. After converting a test example source code into the graph, we can construct a vector representation, and then afterwards we pass it to the machine learning classifier. The machine learning classifier first uses a novelty detector to determine if the test instance looks too different. And then finally, it produces a binary classification that says whether it's a misuse or not. In our experiments, we studied 57 APIs. These APIs range from APIs from the Java standard library to APIs from third-party libraries. For each API, we first collected an average of over 2,300 usage examples from GitHub. In total, we required about 2 iterations of labeling on average, and for each iteration, about 23 examples were labeled. So in total, there were about 50 examples that were labeled for each API. And here's our experimental results on MUBench. In the first half of this paper are API misuse detectors that only use examples from a single project. So in the prior work, in the state-of-the-art approach, it was shown that by using examples from GitHub, MUDetect XP could outperform the existing approaches in terms of the precision at 20 and in terms of recall. Our approach, ELP, outperforms MUDetect XP by making use of the principles of active learning and by using classification with the reject option. We also experimented on a different data set that we termed the AU500. This is a data set of 500 API usages collected from projects across GitHub. In this data set, ELP outperforms MUDetect XP, and we also conducted an ablation study to understand the impact of the reject option. Using the reject option, ELP attains a higher precision and leads to overall a higher F1. In summary, we have looked at the problem of API misuses. Our work builds on top of the insight from prior work that showed that finding patterns from projects across GitHub is a promising direction, but we do not rely on the assumptions relating frequent patterns with correctness. Instead, our approach ELP uses active learning to direct human attention to informative and representative for the human annotator to label. We optimize for the selection to label based on the principles of active learning. And we also use a novelty detector for the paradigm known as classification with the reject option. This paradigm allows us to refrain from predictions that we are uncertain about, and we use a novelty detector to determine if a testing instance is too different from the training instances. Our evaluation shows that ELP outperforms MUDetect XP. Thank you for your time.